Okay, so that kind of wraps up our, I guess, introduction to the concept of internal flow. What I want to talk about now is internal flow correlations and internal flow energy balance. So we're going to go through and think a little bit about how we actually use internal flow correlations that we develop, what they mean, how you access them at ease, how to really interpret the results, and then hopefully by the end of today we'll be able to apply those to a situation where we have a changing state of internal energy in an internal flow. Okay, so the internal flow correlations are kind of come in, let's say, 4 flavors. 2 main groups being, one group is the friction factor, one group is the Nusselt number, and then within those 2 groups, you have a division between local versus average quantities. So the first thing to think about is, let's look at the friction factor first. So normally, if you remember your fluids class, we express the friction factor in terms of something called a Moody, or sometimes called Darcy friction factor correlation. Friction factor. Okay, and so this is going to be for local. So for local, we're going to have that look something like our friction factor is going to be equal to minus dP dx times 2 dH, the hydraulic diameter, divided by rho mean velocity squared. Okay, so the friction factor is giving us something about dP dx, so the rate of pressure loss as a function of position at a specific position, right? At some specific location within the flow, the internal flow. So getting back a relationship for dP dx. For the average quantity, average, we would see something like F bar, and F bar is going to be expressed as either the pressure at x equals 0 minus, say, the pressure at x equals L, so some absolute pressure difference across the flow, times the momentum part of it, which is, again, 2 dH over rho um squared. Or equivalently, sometimes it's just left as delta P. Same thing as px0 minus pxl delta P times 2 dH over rho squared. So that's going to give you, now a correlation is going to be giving you the average pressure drop between 2, average friction factor between 2 locations. It helps you then compute the pressure drop. Okay. And then maybe the difference is obvious, or maybe it's not, but the difference is really that in one case you're getting a gradient back, and in another case you're getting an absolute pressure difference back between 2 locations. Okay, so if we plot out actual correlations for the friction factor, it's going to look something like this, where you have, all right, our local friction factor here at the leading edge, where shear stress is infinite, it's going to be infinite. So right after the leading edge, you see it start up high and drop down until you get to the fully developed point, and then it becomes constant, just like we said before. The average, maybe it's a little counterintuitive, but the average is always going to be higher than the local. And why is that? Well, if you take the integral of the local, which starts off at infinity and then quickly drops, the average kind of remembers the fact that it started off at infinity. So it's always going to have that really high starting point, and then you're incrementally moving it lower as you add more local friction factor to it. So you always are going to have a higher value. And once you get to the fully developed point here, it's not like F bar magically stops changing. It has that memory of the developing region, and that becomes less and less important the further you go out. But eventually you're going to converge to the same thing. But it would be a mistake to evaluate your local friction factor in the fully developed region and call that your average, unless you're sure that you're far enough away from the entrance region. Yeah.
Is that the average for delta P from x equals 0 to x equals n?
So that would give, so the friction factor would give you the coefficient that you need to compute delta P. as opposed to the coefficient you need to appear to compute a local dpdx. So if you integrated this, you would eventually get to this.
Yeah. Where L is not fixed. Once it's variable.
Yeah, so if you integrate it in terms from 0 to some position x, which here we're calling L. Yeah. Okay, so that's the friction factor. The other thing was the Nusselt number. So we have our local Nusselt number, and that's in terms of hydraulic diameter is going to be H and it's D sub H, which is the hydraulic diameter divided by K. So that would give you the local Nusselt number. H D sub H over K. Sorry, I think there might be a typo here. So the local Nusselt number should be, sorry, let me come back to this. So the average should be Nusselt bar is equal to, oh no, I'm sorry. So this is just definition. Let me start this over. So we have our local. Okay, we're just saying that our local, we're calling that Nusselt. That's going to be in terms of a local heat transfer coefficient here with H. So just a definition. So local Nusselt is in terms of local H times dH over K. That's just our definition. And we're defining the Nusselt in terms of D sub H, or hydraulic diameter, D sub H, because it's a convenient quantity. And ultimately, it ends up being a good descriptor of the boundary layer. So that's our local, and then the average is Nusselt bar is equal to H bar dH over K. Okay. So just definitions again. And if we plot that out, it does something similar. We start off our Nusselt number really high. The local, the local goes down, eventually becomes stable, and then the average is always going to be high. Okay, so one thing you're often asked to do is look in ease and use a correlation. So just want to point out where these things are. So if you go to options and function info, sometimes you have to pick it, but you have to pick this heat transfer fluid flow toggle, and then from this drop down you want to pick convection, right? And that's true whether you're doing friction factor or Nusselt. So you pick convection, and then you want to go through, and in this drop down you want to pick the situation you have. I think by default that's internal flow dimensional. So you could look through, and based on whatever your system is, you could pick one of these. We'll start here with a circular duct, but you can see here that it's what are the things it's asking for. It's asking for temperature, pressure, mass flow, DL. It's asking for specific dimensional quantities. If you want to do this, which I would recommend for your own understanding in terms of non-dimensional quantities, you would choose the non-dimensional option. Now it's going to ask you for Reynolds number, Prandtl. You would then have to compute what these things are and put them in. If you're ever curious about the definition, you can look at the inputs definition. So it says Reynolds number based on properties evaluated at the bulk temperature. It'll say, so it's average, so you have to define this in terms of the right dimensions, but it'll kind of give you guidance on how to do that. Okay, so that's interesting, fine. So we get back from this correlation, we give it Reynolds, we give it Prandtl, we give it length over D, so that would be the length of this pipe over the hydraulic diameter. And then we get back something like Nusselt T, Nusselt H, and F. So let's see, if I paste this in here, so I would want to give it these things. There's some maybe confusing things. So what is the difference between Nusselt T and Nusselt H? One is specified surface temperature. So this would be the Nusselt number in the case that the duct that you have has a fixed surface temperature. The other would be a Nusselt number in the case where the duct has a fixed heat flux. Okay? So those are actually two different solutions, because in one case you're fixing temperature, in the other case you're fixing a gradient, a dt, dy. But those are both given to you. And then F is the friction factor. So this one, actually, we want to look and see, right? This one is internal flow, non-dimensional, you notice that they don't say if it's local or average, but they do specify here for the local one. So if they don't specify, you have to assume it's an average one. Okay, so if we wanted to do the local one instead, we would bring in, let's see, let's do the non-dimensional local. So here you can see it's asking for Reynolds, Prandtl, now X over D. So it's going to be my local position X over D and relative roughness. And it's going to give back local quantities similarly. So if you decide that you don't want the constant heat flux one for whatever reason, you can just remove that from the argument list. Oh, that's really hard to see. You can remove that from the argument list, and it will then just not return anything there. You still need to have the commas. You still need these commas in the right order. You just remove the argument physically. So those are the correlations in E's and how you get to them. I think that's probably something you guys have all done by now, but sometimes there are a few subtle points here that people don't get. Any questions on the E's stuff? No? Okay. Let's go back here. All right. So I think it's important for you guys to understand when we're talking about these correlations, what are they actually doing? It's one thing to go to E's and get a correlation out and plug it in and then just say this is what it is. But I think it's really important to understand what they're doing and why different sort of outcomes from a correlation actually happen. So what do I mean by that? I guess there's these different categories that E sort of automatically handles. Like E is if you plug in a Reynolds number, and that Reynolds number is over the critical Reynolds number, it's going to give you back the correlation for the turbulent region. Or if it's under the Reynolds number, it's going to give you the other one. Sometimes you don't even know, based on your calculations going in, what it's going to be. E automatically handles that. But if you look at the behavior of turbulent versus laminar, for example, it's really a fundamentally different behavior. Different things that are governing the results of the correlation. So let's just take a quick look at, this is the friction factor. We'll do the same thing for the Nusselt number. But this is something you almost certainly saw in fluids, but maybe didn't really appreciate what was happening. So let's see. So let's look at this. This plot over here gives us an example of flow in a circular duct. And so we have two things. We have our local friction factor, we have our average. I believe this is giving us back our fully developed friction factor. So this is going to be not just local, it's actually the fully developed, it's only in the fully developed region. So if you had a flow that was still developing, this is actually not quite the right thing. It's just in the fully developed region. So what are we doing? We're looking at, as a function of Reynolds number, what are the different friction factors for different geometries and surface roughnesses. Okay, so over here on this part of it, we have these basically constant lines on a logarithmic plot, and those are saying, okay, if I have a square duct, my square duct friction factor is definitely a function of the Reynolds number. It is changing pretty steeply with Reynolds number. But you'll notice that it's actually not changing with surface roughness. There is no additional curve for surface roughness. It does depend on the shape. So I have a different one for square versus circular versus parallel plate versus annular. But I have different curves for those in the laminar region. So once I get to the turbulent region, though, things fundamentally change. You have totally different considerations now. You see over here, there's no separate lines for square duct versus circular tube. There's no separate lines. Once you get far enough out, it actually stops depending on the Reynolds number. But you do see that there's a really big dependence on the surface roughness. All these different plots that you see are just expressions in terms of surface roughness. So you go from a situation in laminar flow where the duct shape is really important to turbulent flow where it's not at all important. Okay, so why is that? And let's look back at the velocity profiles. That maybe helps understand a little bit. So if we look at our velocity profile in a duct for laminar flow, what does that look like? It looks like this, right? So we have, this is our flow profile. If we have in turbulent flow, it's going to look something like this, where we have a really steep gradient near the wall, and then it's pretty flat. And we have another really steep gradient near the wall. So why would surface roughness not be important in laminar flow? Because the gradient here, this velocity gradient as a function of y is much less than it is in the turbulent region. So you have very little movement of fluid near the surface to begin with. So little features on the surface actually don't become important. They don't actually affect the friction factor. That gradient remains pretty constant regardless of the surface roughness. It is, though, important. You see that there's still gradients as you're going further out into the flow. So the shape of the duct is going to be important in determining the overall shear stress on the surface because it plays into how much room that auger there has to grow. Okay, so then, on the other hand, for the turbulent flow, you see there's a really steep velocity gradient here. That means a little disturbance in the surface, right? Right at the surface is going to have a big impact on the overall shear stress. It's going to have a big effect on the friction forces in the flow. Okay, so you see these different things going on, and eventually you get to the point for turbulent flow where the features are big enough that everything just collapses down to a single curve, right? You could model a square duct, a round duct, you can have any shape you want. It just, if it's rough enough, it collapses down to a single curve. And that all just comes out of the fact that the velocity profiles are really big. Let's see. Let's think about this for the thermal considerations as well. So again, we could sketch this out over here. So we sketch this out for fully developed Nusselt number. Again, in the laminar region, you see that there's square duct, parallel plate, etc. Those things actually do matter when it comes to predicting the Nusselt number from the plate. And then once we get into the turbulent region, the same thing is happening. But now we have surface roughness and we have Prandtl. So if you remember back, I think it was not last time, the time before, where we were looking at how the molecular properties near the wall really actually play an important role because of that viscous sublayer in turbulent flow. So if you have a high thermal conductivity right next to in the fluid next to the wall, that's going to give you a low temperature drop across that viscous sublayer. That Prandtl number actually is really important in governing heat flow in the turbulent region. So here, okay, so we see Prandtl number. We have groupings based on that. And then we have the laminar flow. See a couple things to think about here. One is kind of interesting. So here, there is no dependence of Nusselt number on the Reynolds number in laminar flow. It's fully developed. It's not changing as a function of position. There is no dependence on Reynolds number until you get to the turbulent flow. We could actually kind of ballpark predict these values based on a really rough analysis. Let's just sketch that out really quick. So if we were to want to compute, let's say, Nusselt number in terms of a hydraulic diameter for a duct, we might say that that's going to be Nusselt equals H times D sub H over K. So if I know the rough size of this duct, the boundary layer is going to be able to go to say DH over 2. So I would describe this as what? So K over delta T laminar. This is my heat transfer coefficient times D sub H over K. That's going to be approximately equal to what? D sub H over delta T. So delta T laminar. Okay, so sorry, that's a really simple analysis. What I'm saying is I can approximate my Nusselt number in the laminar region. If I know that my boundary layer is approximately what K over delta T, as delta T over delta T lambda, or DH over delta T lambda. So what is that in a duct? Well, that's going to be something like DH over delta T is going to be nothing more than, say, DH over 2. And from our previous understanding of the actual profile, which is more like a quadratic profile, it ends up being something, more like delta T over 4. So actually, this Nusselt number is approximately going to be on the order of, say, 3 or 4. Okay? Just based on this rough analysis. And if you look at the values, and if you go to ease and pull up the correlations, they're all kind of in that region, that same region, 3 to 4. Right? So that's where that's coming from. It's just maybe something we didn't talk about before, but that's where you can really get a handle on what's happening in the laminar region.